Welcome to another video lecture of OpenStack's astronomy. And in this video, we'll be looking at Chapter 5, Radiation and Spectra. So we'll begin in 5.1 with the behavior of light. And so astronomy is a bit rare as a science that we're not actually able to go to most of the objects we study and manipulate. So we can't go to a star and observe it, gather things there, and run experiments on the star. So we have to find clever ways to try to gather that information. And one way is looking at light and the behavior of light. So here's an image of the sun, but not invisible light. This is ultraviolet light here. So we're kind of looking at a different portion of the spectrum here. We're not able to see ultraviolet, but we do have telescopes and other instruments that can. And so using those instruments, it allows us to be able to see more of objects that we probably couldn't see with our eyes. Credit goes to Maxwell, specifically his theories of electromagnetism. He unified the rules that kind of govern electricity and magnetism into one theory. So it's because of these rules that we're actually able to make relationships and study light and get so much information from them. So let's talk about the dual nature of light. So perhaps you've been on by a steady piece of water, a pond or a pool, and if you throw a pebble or something inside of it, it'll create these ripples. And so much like water, light also behaves with this dual nature. Working together, we see that in these ripples that water behaves like waves. Or going to the ocean, you could see just large waves that kind of come at you, sets of waves. But you could take it apart and look at water as just droplets, so individual droplets. So light has that same characteristic, where we could look at it as little droplets, which are called photons, or we could look at it collectively as waves. So this brings us to a double slit experiment. This is a famous experiment here that has some interesting results. So if we look at light particles, individual photons, so you turn on a light source and you look at photons, and if this experiment starts off where there is two slits, and so the photons will travel through one of those, and then on the back here where they hit, there's an optical screen that will kind of record where they land on. And so if we look at individual photons, so we keep track of the journey of this specific photon, we could see it goes through the bottom slit and it's going to make a mark. And if we let this go photon by photon, we'll be able to see that on the optical slit, what we'll end up with would be two lines on that slit there, so indicating that photons went through one of the slits, hit that optical screen, and we could keep track of them. So Heisenberg's principle of uncertainty tells us that we can't always know the everything about particles. So if you know its position, you're going to know less about some of the other characteristics that it has. So here, if we're looking at the position and we follow each photon and we keep track what slit it goes through, we'll see that we get two lines there. Now, we do the same experiment, but rather than just doing a photon at a time, we kind of open the floodgates. And we don't keep track of the photons. What we do is we just look originally where this starts, and then we look at the end result. And what happens is that if we don't observe which slit the photon goes through, what tends to happen is that it appears that they behave collectively as a wave. So kind of like water crashing through a wall that has two openings. We'll see that it will create these nice ripple effects there. And where the ripples actually meet, you'll get these larger waves, and then where they actually sink in, you'll kind of get these crescents here. And so what happens is, where those waves meet, you're going to end up with darker slits where more of those photons end up hitting. And what happens is, rather than two slits, we end up with many of them that coincide with how a wave would react. So we see that light behaves with those two characteristics, if we're observing it closely or if we're not. So light has these dual characteristics. So as a wave, this crest is going to be our high point, and then the trough is what's considered the low point. And the wavelength is from crest to crest, so this distance here. And so we call that, how often a crest comes in, or if you're at the beach, how often waves come in at you. That's what we consider the frequency. So how frequent those crests come in. So individual particles of light are called photons, and they also have wavelength and frequency, and the energy and frequency are dependent on one another, so they're related. So as one goes up, so does the other. So for the more mathematically inclined, here are a few relationships here between wavelength, frequency, and energy. But in short, the shorter the wavelength, the higher the frequency, and same for these photons. The shorter its wavelength, the higher the photon energy. So looking at this mathematically, lambda here is the wavelength, and c is the speed of light, which is a constant. So if the product is going to be constant, we're not going to change what that is. Then if you make the wavelength smaller, then the other factor, or the frequency, has to compensate and get bigger. And we see that here as well with the energy here. Here H is going to be a constant. So the shorter the wavelength, the higher the frequency will go. So that will go up. And then if we're multiplying, then that means the energy will also go up as well. So propagation of light here. So we're aware of some properties of light, and how do we actually use that when we're looking at stars? So stars are radiating light in all directions. We only see a small portion of that. So for example, let's say that we're looking at light from a star. If it goes out 1 light year, let's just say 1 AU, then all of the area that we see here, the light that we're going to look at would be focused on 1 square here. So we could say that that's 1 AU by 1 AU. Well, if it keeps traveling, say it goes out 2 AUs, now the area that's created there is going to be wider. So that same amount of light is now spread out. So the further that you are, the more spread out that light is across that area. So when we detect this intensity, this energy of the photons, we have to calculate for that, right? Our distance of how far we are and how much we're getting. And then we could reverse engineer that, and we could calculate how much of that light is going out in all directions, because all we're seeing is one single, we're just getting it from one single direction. So it gets spread out all the way through. And so this is a relationship here between the distance and then the energy that we get per unit. So 5.2 will explore more of the electromagnetic spectrum, which is a larger spectrum here. We are familiar with visible light, which is a very small portion of it. Our eyes evolved around the sun, which is yellow. So we evolved looking at visible light. but there are more wavelengths there. These get smaller and larger, the wavelengths here. We could go into infrared. Or even microwave and radio waves, or the other way, ultraviolet, X-rays, and then gamma rays. Now, our eyes are not able to detect that, but those waves are traveling. So much like a radio, those wavelengths are passing through. You don't see them, but yet your radio is able to detect them. Sound waves in a similar manner there, where you're able to hear higher frequencies, lower frequencies. They're traveling, but you're unable to see them. And depending on your receptor, you could hear higher pitches or lower pitches. So bass frequencies and that treble. And so the light behaves in that same fashion there. So for us, we don't want to just look at visible light. It's helpful to have instruments, mainly telescopes, that could detect these other frequencies in the electromagnetic spectrum. So our atmosphere protects us against some of these or some of this radiation. And we could see here on this image that gamma rays here don't make it quite all the way through because our atmosphere is helpful to protect with some of that. Visible light makes it all the way through, and we're actually able to see that. Radio waves, these longer waves, also make it all the way through. But there is a lot of the electromagnetic spectrum that doesn't make it all the way through to from the atmosphere. And this is why we like telescopes out in space orbiting around the planet, because they're above that atmosphere, and it helps us detect all of the spectrum. So how does light interact with matter? It interacts in one of four ways. Emission. So if you are turning on a light bulb and that's radiating light, right? We're able to see that. Transmission, if it goes through some type of medium, so passing through a glass or a window. Reflection or scattering, so again going through a mirror or perhaps even snow, it's able to reflect that. And then absorption. So when we look at a chair, perhaps a red chair, that chair actually is every color but red, right? It absorbs all the other colors, and it seems to kind of throw out, it scatters that red light more than all of the other colors. So four ways that light interacts with matter. And also light, if you've ever been next to a light bulb, right, it creates heat. It's a sense of heat source. So those different wavelengths are going to be attached with different temperatures. So here we see that red light is actually a lot cooler. It peaks out at about 3,000 degrees Kelvin. And when we talk mainly about gases or so, a lot of times we use Kelvin as a unit, very similar to Celsius. So we'll stay away from Fahrenheit and Celsius. We'll introduce this new unit of Kelvin, degrees Kelvin. And when we talk about stars in our part 3, we'll look at some relationships to kind of get a sense of scale. But red light is actually cooler. Going to yellow starts heating up a little bit, then green light. And the hottest is actually going to be that bluish color. So blue light is actually hotter. It's going to peak out with an intensity a lot larger than red light. So we typically think of hot as red. But next time you're around your stove, if you see it turned on, it's going to create blue flames, not red, because it gets hot instantly, extremely fast. So blue is going to be a lot hotter. If you're looking at something like a bonfire, it'll have red flames, but it's not going to be nearly as hot as blue flames. So now this is going to allow us to further explore this spectra of light. So we're able to know some characteristics of light, a relationship as far as temperature, right, and its behavior. When we start looking at it in terms of wavelengths, we know energy, intensity. And next time, you're outside at night, look up, and you'll be able to see that some stars look a little bit more reddish in color, and others look a bit more bluish in color. And so if we're able to get a coloration from that, those photons that leave those stars, that's going to allow us to now start attaching some temperature to those stars. So looking at the entire spectra now, what we see is that there's 3 different types of specters when we collect light. If you pass light through a prism, it'll break it up. That white light will break up into visible light. So all the colors of the rainbow, so to speak. And they will make a continuous spectrum. But when we observe objects in space, we don't always see that continuous spectrums. Sometimes we see a bright line spectrum where most of the spectrum is missing, except for a few key lights there or frequencies, or a continuous spectrum here with these dark lines here, so dark line spectrum. And in this case, we just have a few that are actually missing. And sometimes this is called an absorption spectrum. So let's look at the continuous spectrum. This is if we're looking at an actual source, so like a light bulb. We're looking at the entire visible light without any interruption. We'll get the entire spectrum. If we're looking at an emission spectrum here, where we're only going to detect a couple of these lights here, in this case, if we're perhaps looking at space at a cloud of gas, which doesn't have that much light in it, so this cloud of gas will be able to look and it will give us an emission spectrum. So just looking at a couple of these lines here. And then for that absorption spectrum will be as if we are looking at a source, perhaps a star, behind a cloud of gas. And so now the cloud of gas will block some of that light, and that's the absorption. And so if we're looking at the light source, we're going to be missing a couple of those lights in the spectrum. And this is similar that if we're looking at that cloud of gas, likewise, the actual spectrums that are, or lines that are missing in the absorption and the emission will be the same. And so these formations of the spectrums are actually related to energy levels or ground states of atoms. So these atoms, these electrons that are around it get ionized. So we'll put on kind of our chemistry hat, but we won't go too much in depth there. And so what happens is when these get ionized, they're able to jump energy levels. But there's certain energy levels that they're allowed to jump. So for example, if you're going upstairs, you could take one full stair, or you could maybe perhaps use 2 stairs, depending how long your legs are, or maybe even take 3 steps at a time. But you can't take half a step, right, or 2.5. You're going to have to take whole portions. And you might not be able to take 10 steps at a time because your legs are not long enough. So similarly, when these electrons get ionized, there's only certain levels that they could jump. So they might be able to jump to a first level, a second level, a third level. And so these levels are associated with different wavelengths. And so these spectrums, these absorption lines and emission lines that appear in them are specific wavelengths that are attached to it. So every element has kind of like a fingerprint that is unique to that element. So for example, in this case, we're looking at hydrogen. Well, when those electrons get ionized, there's only specific levels that it could jump, right? its legs are only so long. There's only specific number of steps that it could take. So when we look at hydrogen, we will always see at 656 nanometers or 0.3 nanometers. We will always look at 486.1 nanometers. So it's these specific ionized markers that we always see that are unique to hydrogen. Every element is going to have its unique levels that the electrons get ionized. So when we start looking at a cloud of gas or some light source, and we start looking at these emission and absorption spectrums, and we see which lines are missing, then we could say, hey, this element is attached to that. And this is how we could detect that stars are made up primarily of hydrogen and helium. Also is what is considered a Doppler effect that's associated with these wavelengths. So as we collect these spectrums, there's also this Doppler shift. So if you've ever been in a car when an ambulance is passing by, that pitch sounds different when it's coming towards you and away from you. So when an object is coming towards you, you're going to get a blue pitch, which means that those frequencies start getting pushed together. And when it's going away from you, it kind of has to play catch up. So those wavelengths are going to get spread out. So the same thing happens with the spectrum. So if we look at something like hydrogen, when it's stationary, these specific lines here should be at specific wavelengths. But what happens when we actually observe them is we see that all of them get shifted over slightly towards the red. And if they're all shifted over towards the red, we say that an object is moving away. If it's shifted further to the red, then we know it's moving away at a faster rate. Likewise, if they're shifted over towards the blue, we call that a blue shift. And the further the blue shift, the faster it's moving. So just by looking at light, we're now able to associate temperature to it. We're also able to now figure out chemical fingerprints. So what is it made out of? And then also if objects are moving towards or away from us. And this is why astronomy is kind of considered a jack of all trades. We have to come up with these clever ways, and we have to now know, physics, some chemistry, apart from mathematics, to try to tie in all of these relationships together.